So until the last class, we had talked about ATMs, MPLS, etc. and how they work. Okay. So, and we had ended with the note that, we will check how the telephone network works, because that is one of the basic networks that we had started with, right? I mean, we had, in the sense, the researchers had started with. So today we are going to talk about telephone networks. And what is the basic thing that we know about telephone networks? That it works on the principle of circuit switching, right? That's what we know about telephone network. So let us see how telephone network works. So this is what is written in the first slide here, that what is a computer network. So I will put it in this way, okay, that what we have studied in networks throughout until now, whether it is your BTech basic computer networks course, or even the few classes that you have done in this course, okay. So we know that a computer network is, capable of carrying voice or video data, fax, telemetry data. And how does it send that? It uses digital samples to basically move the data. The data moves in a as a signal through the medium. And then when it reaches the devices, then we use digital sampling, and then that digital data is used by the devices to know that what was the exact data that was sent to you. Because in the devices, it will that is what the basic formula of computer network is, right? So we have seen all of this. In fact, if you remember, in your computer networks course, we had studied something regarding modems. Okay, that is the early or probably one of the earliest ways of accessing the internet by using your telephone network itself. Okay, so there, if you remember, we would have these modems which would be responsible for modulation and demodulation, right? So if you remember that, then you will also remember now that we can have all of these properties in a particular computer network. Okay, so when we talk about a computer network, we know that the computer network is having all of these special properties with it. All right. So one of the important components of computer networks will also become now telephone networking. So we can say that telephone networking is one of the important components of a computer network. Okay. So what does it offer? It offers switched voice service with small end-to-end delays and call completion guarantee. Okay. So we know, right, it is basically using circuit switching. So if that is the case, then therefore we will have very less end-to-end delays. And we know that why we will have very less end-to-end delays. I would ask this question a few slides later again. And then we would have call completion guarantee, because we are giving a QoS guarantee, and we are basically reserving the resources until the call is done, right? So that is basic of how telephone network works and what it offers. Okay, so the QoS that we are talking about is obviously achieved by setting up a circuit between the two endpoints. And here, what do we mean by circuit? It is, of course, a path between the source and the destination, with signals flowing simultaneously in both directions. So it's a duplex connection. Okay. So now the network guarantees enough resources to each circuit to ensure that the service quality is met. Okay. So these are very basic terms and terminologies. We know all of these from circuit switching itself. Okay, that what are the properties, what are the features of circuit switching, and if you use those features of circuit switching in telephone network, so these will be the basic requirements when you want to set up a path between any source and destination in a telephone network too. Okay. What is the big picture that we are about to see? So this is the big picture. Okay, your end systems here are going to be the telephone devices, okay, that you have in offices and in your homes also. Perhaps you will be having landline phones. So these are the end systems that you have in your home. Now how they work? Okay, so these end systems are basically connected to some local offices, okay, which are near to your area. Those are known as central offices. Okay, so these are those components, the central offices, and these central offices are further connected to the network, which is going to be, mm, connecting your or which is going to be your background or core network in between. So that is what we call as the long haul network. Okay, so you have end systems, you have central offices which connect these end systems, and the central offices are further connected to the long haul network. So central offices are basically acting as gateways between the end systems and the core long haul network. Okay, so this is the scenario. Now you can see that this looks as a connected graph. Anyways, we know that when we are talking about networks, we have to ensure that it's a connected graph. So we have a connected core here, and then this core is again connected to the central offices. So routing will become simpler when we have such kind of a scenario, right? So the routing becomes simpler. And now how will you identify that from which source to which destination the call is there? So for that reason, there is a particular identification number for each source and destination, and that identification number is the phone number. Okay, now the phone number is divided into parts. We all know that, right? So those will again define that what are the different offices through which that call needs to be going. Okay, so this is how so that's what the second point is talking about, that is the telephone number is a hint about how to route a call between a source and a destination. But of course not for certain numbers. So here it is given as some 800 or 700, but actually it depends from country to country, right? Like 100101 in India, and then you will have, I think, 911 in the US. So like that, for certain numbers, they do not, you do not have to route the call through particular source and destination. For certain emergency numbers, it will directly connect you to that particular destination, no matter wherever you are from. Your central office, once you dial this, your central office, or from via your central office, the call will be connected to the particular destination. Okay, now as I already told you that the number itself tells about that how the phone call should be routed, and this entire telephone number space is actually hierarchically allocated, right? So you have the IST part, you have the STD part, and then you have the local part, and then finally the 4-digit identification that you get for your own um, telephone number at your house. Okay, so if you check that, if you check the entire phone number of any other country, or if India, if you for the ISD code you have a particular code, then after that for STD you have another 3 digits, and then you have your for that particular locality you have one set of 3 digits which will define that this is the particular central office of that locality, and then that will basically be the identification of the central office of that locality. And then after that, from there you have the last 4-digit numbers which actually define or identify your the device at your home. Okay, so this is the hierarchical allocation of the telephone number space. What are the pieces that basically form this entire system of telephone network? So first is your end systems. We have already studied what are the end systems, but we will study a little bit more on that. The components of end systems basically. So end system is nothing but the handset that you are getting, the telephone handset. Then you have the transmission between the source and the destination. Then you have switching, and then finally signaling. Okay, so we will see each one of these components starting with end systems. Okay, so this is pretty simple. Your end system is that device which is basically allowing you to connect to another destination and also to transmit your voice to another destination and listen to the other person's voice who is trying to speak to you. Okay, so therefore it has transducers, okay, which is responsible for carrying voice on wires. Okay, so this device that you are getting at your homes, that has transducers, it has a dialer, it has a ringer, and it has a switch hook that is very uh, common. Okay, just to keep that device somewhere, either you want to hang it on the wall or you want to keep it somewhere. The ringer, of course, ringer is needed for alarming the user that there is a call. Dialer for allowing the user to dial somebody else's number, and the transducer will be responsible for carrying the voice on the wires. So that is the components of end systems. Now we get to the transmission part. So we know how the transmission will happen. We know that there will be a route that will be allocated before the call transmission happens. So that is done through the central office. And once we know that, what is the phone number, we know that which all central offices need to be connected. So via that route, resource is now reserved, and then after that the transmission happens, right? But how is this transmission happening? What are the link characteristics? How is the propagation delay considered, or how is the propagation delay calculated? And what are the faults for such kind of a circuit that is we are reserving for the communication to happen? Okay, so that is what we are going to study in this part. So let us first see what are the link characteristics for this transmission to happen. So first we need to have a bandwidth. We need to know that what should be the bandwidth. Okay, so there should be enough information carrying capacity, or enough bandwidth should be there. Then the information is basically sent as digital symbols. Okay, and we know that one symbol is around or more than 1 bit. Okay, it can carry more data than that. Then we have propagation delay. So propagation delay, we all know that, how much time does it take for your data to go from one end of the transmission medium to another end of the transmission medium, right? So how are we sending the data here? We are sending it as electromagnetic signals, right? So now if we are considering, of course, an optical fiber, and it has, uh, we know that, it is going to send it as light signals. So therefore it, that how it is going to send, or what is going to be the speed of it. So it is at 0.7 C, and then the fiber will be sending at approximately 5 microseconds per kilometer. Okay, so these are some probable distances that have been given. So like New York to San Francisco, this is the 20 milliseconds is the time. New York to London, it takes 27 milliseconds propagation delay. Okay, so that's how fast your optical fiber can actually work. Now, whatever transmission medium you are using, there will be attenuation, right? If you're using optical fiber, of course, there will be minimum of that. But where will be the attenuation happening? With distance, the signal quality reduces. Okay, that's what the issue is when you are trying to send the data for or the signal for a large distance to a large distance. Okay, so for that, what do we need? We need regenerators for keeping the quality of the signal intact. Okay, so what is there in the regenerator? So we have these optical amplifiers at the regenerators, which basically improve the signal quality when you are transferring the data for a really long distance. Okay, now this is an interesting question that I have. Now you have seen telephone networks for a really long time. You have already studied about different types of computer networks. I mean, you know about different types of computer networks. So we make very long distance calls, right, from one end of the world to another end of the world. So how do you think that this communication is happening? We are actually considering circuit switched networks here, right? So how do you think such a big circuit is being connected, and how the entire world is actually getting connected? So is there some wireless connection in between that's happening, or we do have point to point wired connection throughout the world? So can anybody, just you can guess also, it's not a problem. So can anybody give me an answer to this question? This is just a guess question. What do you think, how it happens, how the transmission happens? Maybe you have seen some movies or something about it. So there are oceans in between, there are so many other lands. So how does this communication happen? Any idea?
From midway somewhere, are we making use of satellite communication, ma'am?
Um, Not exactly all the times. Okay, satellite communication is pretty expensive, and it works in a very different frequency there. Okay, so that is one thing. And any other ideas by anybody else? I'll tell the answer afterwards. Yeah.
Point to point communication.
How does it happen? It's a very big region, right? One end of the world to another.
Wires are connected. In oceans there will be wire lines.
But how do you maintain in an ocean a wired line? It's too big, isn't it?
Yes, ma'am.
Okay, so you are correct too. All right. So we do have very huge, if you were in class, I would have shown you. Anyways, we have very huge kind of coaxial cables. Okay, so they are insulated very nicely. They are coated, they are insulated very nicely, and we have huge set of fibers which are actually run through the oceans also. All right. So most of the communication that happens in the world over telephone network is actually through these wires which are laid over uh, the wherever in the world. All right, so it can be under the oceans also. Okay, and sometimes actually these how this network has been laid down, this is actually kind of a secret, because if some country tries to cut this down, they are actually cutting the communication for another country line. And even sometimes maybe you can tap some secret, we also have the line for different security purposes, your red lines, like to the ministries, to armies, air forces, etc. So those are also, if somebody can tap somewhere in the world, then it'll be gone. So, and that is the reason that you have different kinds of cryptographic technique being used, so that even if somebody taps, it is very difficult to find out the actual data that is being sent. Okay, so it's very interesting when you think about it. All right, so yes, now let's get to the next part. Okay, so how does the transmission happen? Okay, so it cannot be like, you know, there's one wire and you are sending only one signal at the same time. So we try to send more than one signals at the same time. And how do we do that? You already know, we multiplex the data. Okay, so that is what we are going to study in this part of the slide. So two types of multiplexing can happen, either analog multiplexing or digital multiplexing. Okay, so analog multiplexing will be for the analog signals that we are going to transfer. Digital multiplexing will be, of course, for the digital coding that we are doing. Now, analog multiplexing, there are two parts. One is that you know, the bandwidth, the band limit call to 3.4 kilohertz, and the frequency shift is onto the higher bandwidth trunk. Okay, and this is basically an obsolete technique that was used to be done earlier. Now we use digital multiplexing. So what we do, so we convert the voice sample that we are receiving and into the digital samples. Okay, so we are receiving voice signals, we are converting it to digital samples. Now how do we define a sample? Sample is 8 bits of voice. I had told you earlier, right, that one bit is one sample is greater than 1 bit, greater equals to 1 bit, right? So that's what is happening. So one sample is equal to 8 bits of voice. And then how do we calculate it? So if we have 8,000 samples per second, then the call will have a band of or capacity of 64 kbps. It will give you the capacity of 64 kbps in that case. So this is how helpful your digital multiplexing is. Okay. Okay. Now the question is, how should I choose samples? Okay. So samples are chosen with the help of quantization levels. So we can have 256 quantization levels. What are these quantization levels? These are logarithmically spaced, since this gives better resolution at low signal levels. Okay, so one sample value is equal to amplitude of the nearest quantization levels. Okay. Achha, I do have a question. You guys did you guys have any digital courses in your first second years of BTech? Like, are these terms relevant to you, or are these terms not relevant to you at all?
Not relevant.
Not at all. No digital, I mean, basic course you guys have not done in your first or second years?
We learned about gates or gate FSMs, but we did not have the terms quantization.
None of these sampling and bit rates also, nothing.
No,
But you must have done multiplexing, no? Time division multiplexing, space division multiplexing, those?
no, ma'am. We studied in last semester course, computer networks course only.
Oh, in computer networks only you have done time division and space division.
No, not a space division also, only time division.
Space division you will see here, time division and frequency division you must have done. Okay, because I just thought that I should ask this question. Okay. Then going to this basic will be difficult. This is basic digital course. Okay, so what I will do is I'll try to filter out these things. Okay, if you are not understanding this part, then it will be very difficult. So I'll just give you some brief introduction of this then. Okay, let me just see how I can just wait a second. Yeah. I think this can be done on. I think after this, nothing much is there on this. So anyway, so we are using time division we can use time division multiplexing here. You all know what is time division multiplexing. So what happens, the trunk carries bits at a faster rate than the inputs, and if we have n input streams and each input stream is having 1 byte buffer and there is only one in output link, this is happening, multiplexing is happening. Okay, what we know about multiplexing, there can be multiple inputs and single output. Okay, so multiple inputs are here, that is n input streams. Each stream is having 1 byte buffer with it, and there is one output link. Okay, so at the output, what should we expect? That it should be n times faster than an input stream, right? Because n inputs are there, one output link you have to send the data, so the output link should be n times faster than the input link. Okay, now okay, so you don't know about interleaving either, I guess. Okay, now we send the data as a frame. Okay, now please understand this frame is a bit different from the frame that you have learned in your computer networks course. Okay, what we are calling a frame here is that this output link that we are getting now, from this output link we are getting a bit of data stream from n inputs. Okay, so how long will you keep this data stream? Okay, along with some overhead will be there, so that entire stream of data with some overhead, that is known as the frame. Okay, so now what will the receiver do when it basically gets a frame? So receiver will extract the constituents of the frame, which will basically be the data stream that was received from the input side, and then it will how will it do that? It will synchronize itself with the frame boundaries, and then it will receive that data. Okay, so on the whole, if I have to summarize without thinking about this all quantization levels and all these digital terms, so basically we are using digital, we prefer the preferred multiplexing technique is digital multiplexing technique. What happens in digital multiplexing technique? Voice is converted to digital samples. All right, now one sample can be equal to around 8 bits. Okay, now there are several ways of choosing that how big you want your samples. That is done using different quantization levels. You can check yourself what is the quantization level and all. And one of the most generally used multiplexing technique, or one of the examples of multiplexing, digital multiplexing techniques, is time division multiplexing. What happens in time division multiplexing, we all know. Now here how multiplexing is happening, that has been given. That means you can have n input streams, one output stream, and these n input streams can take only 1 byte of data because they have 1 byte buffer. Now with this kind of a situation, the output link should be n times faster. This is an example situation that I am giving you here. So if there are n input links and one output link, it should be n times faster, the output link. Okay, now how does the output link get that data? It gets the data in the form of frames, and with some added overheads with it. You know, you will always have a divider as to where the frame ends, where the frame starts. Okay, some more overhead will be there. Now at the receiver end, when it receives the frame, then what it will do is it will read the content of this frame to understand that what is the end, what is the start of the frame, and what is the data in between. Okay, so that is how we get to know that what is the data that we are getting in the in this kind of a network. All right, so I hope that this made sense. I did not know that this basic was not done. So anyways, I tried my best. If you still did not understand, you can ask me questions on this again. Now let me go ahead with the transmission links. So transmission links are of different types. This already you have studied. We can have, you know, twisted pair cables, coaxial cables. You can have wireless medium of transmission. It can be terrestrial, satellite communication, and you can also have optical fiber communication. Okay, now why do we go for different types of transmission links? Because we want more and more bandwidth. Okay, and we do want less and less cost, but if you want more bandwidth, you have to spend some more money on that. So two popular sets of communications are there. One is optical fiber communication and another is satellite communication. Okay. Now, yes, as I was talking about that we do want more bandwidth with the cheapest link, but that is not always possible. Okay. And why do we, I mean, why is it okay even if your link is not cheap? Because this is a deployment cost that we are talking about. So once you pay a lot of money and you install the link, then after that, you will not have to have much of the maintenance cost. Okay, so in general, in all other kinds of networks, you what we have is we do have the infrastructure cost. That means you deploy the particular device, and then after that you have to continuously have a maintenance cost. Okay, but here when you are considering the transmission links, you just have to put out the transmission links, and the maintenance will be caused like once in a while, right? Like only if there is some issue and you find that okay, at this place there is an issue, only then you have to do a maintenance on that. Okay, so that is why even if it is a costly link, you will gain much more than what you are going to spend on the on any kind of modifications that you need to do. So one of the best links is of course fiber optic links. Gives a lot of capacity, nearly error free, very little attenuation, and it is hard to tap. Okay, so that is why we use fiber optic links. How does it look? We know that it is made of glass, and very thin strand of very pure glass it is. Okay, now on the screen there is something shown that it is a concept that is used in optical fiber. So can anybody tell what is this concept that is being used so that we have very little attenuation?
Total internal
Total
reflex.
internal.
Yes, can anybody tell me how it works?
When the angle of incidence is more than some certain amount of angle, then it reflects into the same medium.
What is this some certain angle?
Critical angle.
Yes. Okay, so who said critical angle? Can you define critical angle? Just basic how, what is critical angle, why it is needed? Anybody else cannot sorry, anybody else can also answer.
Ma'am, whenever the ray incident from the one medium to the another medium, then their refractive indexes are different, right? So whenever
Yes.
their relative refractive index is inverse of that relative refractive index is more than one, then
Mhm.
the ray will be reflected.
Yes, I was just asking what is critical angle.
Ma'am,
Yeah.
sine inverse of mu1 by mu2.
What is mu1 and what is mu2?
Ma'am, mu1 is the less denser medium and mu2 is the more denser medium. Uh, means in medium through which the ray is coming, that is uh, mu2, that is higher denser medium.
Mm-hmm. So basically during the refraction you get to know that from one medium 1 to medium 2, which one is the denser medium and what is this angle, I mean how this refraction will happen, and from there you can get the critical angle, right?
Yes, ma'am.
Okay, so this, I think all of you are very much aware of total internal reflection, so I will not get into what is total internal reflection. So this is how the optical fiber cable will look like. So you have a padding here, insulation padding, that is known as cladding, and the signal is actually going through the core. Okay, so there is enough insulation, and of course you're using the material that you're using for the optical fiber, the glass material, so that will cause total internal reflection, and that is known as the core here. Okay, so that is why it is known to have very little attenuation, nearly error free, and hence it will have a lot of capacity associated to it. Okay, now let's get to another mode of communication, that is satellites. So satellites of course help in long distance communication but still give very high bandwidth. Okay, so that is why satellite communication is also important, and it is also thought of like it can be used, but it is not always chosen as the part of medium. Okay, so anyways, there are different types of satellites. We have geosynchronous and non-geosynchronous, that is low Earth orbit satellites. So geosynchronous satellites are are placed around 36,000 kilometers from the Earth, and their propagation delay that you get is around 250 milliseconds. Okay, so because 250 milliseconds is quite high, they are not good for interactive communications. Okay, now we go to the low Earth orbit satellites, that is non-geosynchronous satellites. So non-geosynchronous satellites, um, for them, even though you get a better propagation delay and better bandwidth, but there is a concept which is known as handoff. Okay, that is moving from one kind of node, when the signal is moving from one kind of node to one node to another node, that is known as handoff. Okay, so when your signal is trying to move from the satellite to one particular node at the Earth, and then it moves to another node, so this handing off of the signal from one node to another, that becomes pretty complicated in case of low Earth orbit satellites. Okay, so that is why here the complexity is also pretty high. So we have to make, so as either we want a high bandwidth or we want more complexity, or whichever one you want to avoid, basically, that whether you want to avoid high complexity or whether you want lower propagation delay. And then you can also consider that, okay, fine, is it feasible to put a fiber link? If it is feasible to put a fiber link over two particular lands on Earth, then whether you will go with that or not. So whatever is feasible at what point of time, that is used, and that is how we generally have all the communication links over the world. Okay, because the need is that, whether it is the telephone network, whether it is your internet, whatever it is, the need is that it should be a connected network. Okay, that's important thing. So always remember, you should have a connected network, so that if one link fails, you do have another link to connect. Okay, so if you are trying to have a transmission medium, you should have a kind of transmission medium, whatever is feasible to you at that point of time. So in general, as I was telling you in the beginning of the class, that the most preferred transmission medium still is the wired medium. Okay, right. So let me just drink some water, just give me 1 second. Okay, now we are going to do switching. Okay, so switching of the data from one point to another. That means, see, you remember in computer networks you had forwarded the data from one switch to another. Okay, but here what you are going to do, you are basically connected from one node to another. But here what you are basically doing is that you are trying to connect one node, that means your end system, to a particular link. That is known as the switching here. Okay, so as in every other network that you have done in the router section, we had done in the class, right? That router has a control plane and then we have a data plane. Control plane is used to have, you know, to basically manage all the control information. Data plane is used for the actual task of, you know, forwarding the data and all that. Okay, so here too we have two different planes, that is control plane and data plane. Okay, so as you see, the data plane consists of the switch hardware, the end systems, etc., and the switch hardware is associated to a switch controller. Okay, so this forms the switching system, the switch hardware with the switch controller and the end systems. So they form the switching system because that is where your your call that you are trying to make from your system, from your end system, is going to get switched or connected to the actual path. So at this point itself, you know that, okay, this guy has made a call to a particular guy in Hyderabad. Being done here. Okay, so this is what is the job here. So that is why there is a
Ma'am, your voice is not clear.
between the control and the data plane here. Oh, my voice is not clear. Okay. Um, just a second. Let me check once.